Get started. We're talking about geometry of multiple images, and in particular, we're talking about epipolar geometry. Okay, so remember that we consider two cameras. Each one giving us a virtual image that's in front of the pinhole. So here's one, here's the other. And I'm going to consider the pinholes to be here. Let me call it O, and here O prime. And I'm going to have a capital P vector here, which I am looking at or projecting onto each of the two cameras. And therefore, I have three vectors. The OP vector that connects my pinhole of this camera with the three-dimensional point P. The O prime P vector that connects the second pinhole to the point. And this one, which is O prime vector. And that defines a triangle, right? In three-dimensional space. And that's why this is sometimes called triangulation. So we showed that I can compute this cross product of O prime, oops, sorry, I forgot to write small p and a small p prime on my two images. So I can call this image a plane pi, and this one pi prime. So if I do the cross product of O prime with O p prime, that's going to give me the normal vector to that plane defined by that triangle. So if I now multiply this by a vector that's on that plane, on that triangle plane, or the plane defined by this triangle, then the inner product is going to be 0. So what I'm going to do, I'm going to rewrite this as a translation. And I'm going to rewrite this vector here as my rotation. So in that manner, I can simplify this as P, this equation that I have here, as P times T cross product R P prime equals 0. And now I'm going to define a new matrix called the essential matrix, remember, which is nothing else than this thing right here. So I'm going to define it as T sub X times R the rotation matrix, and T sub X is the skew symmetric matrix that we've defined, which is equal to 0, negative T3, T2, T3, 0, negative T1, negative T2, T1, and 0. Okay? So this is a symmetric matrix, but it is skewed because when on one side of the diagonal it's negative, on the other side it's positive, and vice versa. Right? And with that trick, we can convert this cross product that I have here into an inner product. Okay? All right, so with all this, we were able to simplify this equation here as my point my image point P times the essential matrix times P prime equals 0. And that's the equation we want to work with. And again, remember that we're assuming the cameras, these cameras here, are already calibrated. All right, so what do I need to do to understand the three-dimensional world that I have there? I need to know where these two cameras are with respect to one another. Okay? So remember, I need to know that one camera is given by a coordinate system A, and another one is given by a coordinate system B, and I need to know the transformation between these two coordinate systems. Right? Now, if I'm given a certain number of image points, right, in these two images, I have a set of equations that I can solve with a method that we've seen called linear least squares, right? And I can solve for this matrix E. We're going to do that in a second. But now the question is, once I have E, then what? How am I going to go from the essential matrix to the translation and the rotation that I'm interested in? So let's see this. And this is a result due to Longet-Higgins. And I am going to give you, published in 81 in the journal Nature. And I'm going to post this paper in Carmen. I usually say that you are not a researcher in image processing or computer vision if you have not suffered through the reading of that paper. So I'll post it online, you read it, then you tell me whether I'm right or not. Okay. It's an essential paper. I mean, it's truly amazing. It's one of the most important papers you'll ever read in this area, but yeah, it's just hard. All right, so let's see how we can do this. The first thing that I'm going to do, I'm going to compute the essential matrix times the essential matrix transpose. This, of course, I know, right? The essential matrix is this thing right here, you see? So this is equal to TXR, right? That's what I have here, times TXR transpose, which is R transpose TX transpose, right? Yeah. And look what we've got right here in the middle. R times R transpose. What's this equal to? Remember? The identity matrix, which means that this is nothing else than TX times TX transpose, right? And what's TX transpose? Well, I don't know, but I know what TX is, so I can compute that. So let's do this computation. So I'm going to do TX multiplied by its transpose, right? So I have here, I'm going to get T3 squared plus T2 squared, right? Because it's this one times this one. I'm going to get 0, T3 squared, and T2 square, right? Right? Because it's this one multiplied by itself, right? Okay. And negative T1, T2, negative T3, T1, negative T1, T2, T3 squared plus T1 squared, negative T2, T3, and the final column, I'm gonna, can I fit it here? There we go. I'm gonna write it on this side, negative T3, T1, negative T3, T2, and T2 square plus T1 square. Okay? All right. Great. Now, remember what we said about system of homogeneous equations? What did we say about our solution? Up to scale. Okay, so the solution is going to be given up to scale. So let's choose a scale. How about T1, the 2 norm, T1 plus T2 plus T3 square, it's equal to 1. Okay, how about that? That's the norm 2 of my vector T equal 1, right? That's my scale. And of course, that's the classical assumption that we like to make. So if I do this, I can rewrite this matrix as follows. 1 minus T1 square, negative T1 T2, negative T3 T1, negative T1 T2, 1 minus T2 square, negative T2 T3, negative T3 T1, negative T3 T2, and 1 minus T3 square. Now all I've done is I have used this knowledge to change the substitute here, right? So T3 plus T2, T3 square plus T2 square is equal to 1 minus T1 square, right? From there, and so on. So I substitute this. And now look at what happened right here in the diagonal. I have 1 minus T1 square, 1 minus T2 square, 1 minus T3 square, right? So from this new matrix, E times E transpose, I automatically get the values T1, T2, and T3 in the diagonal. Trivial, right? Okay. So that gives us the translation. We already know that from this E, I can recover the translation. Actually, not this one. I can recover this translation. Okay? So far, so good. Now we need to recover the rotation. See how we can recover the rotation matrix. Now, E1, remember that we like to take the matrices into components, E1, E2, and E3, the 3 rows of R. E1 is equal to, let's see, it's R1 transpose cross product with T transpose, right? Because R, as always, right? Remember R was R1, R2, R3, right? The 3 rows of R. Then I'm multiplying this by Tx. Where is this? Right here. I'm multiplying this by Tx transpose, right? So R1 times Tx transpose. This is going to be equal to the first row of E. The second row is going to be the same, but for E2, R2, excuse me, R2 transpose times T transpose. And E3, it's going to be equal to R3 transpose times T transpose. Right? And I have one more equation. Anyone can tell me what the additional equation would be? Because I know something about the rotation matrix that allows me to write yet another equation. What do I know about a rotation matrix? What's that again? Very good. So they are orthogonal vectors, right? Orthonormal vectors, the vectors that define the 3 rotations of R. So I can also write that R1, or I'm going to use Longet-Higgins notation, the rotation of one of the angles, say alpha, has to be equal to the vectors that define the other rotation, so I can write this as W beta cross product W gamma, if you will. And maybe you can add something here, but it's relevant. But this is what we're interested in, that the cross product of two vectors, right, has to give me the orthogonal direction. So meaning I only need to solve for two of these equations. So remember T, I already have it. T, I already have it. This is also known. This I can compute. And this one I can compute as the orthogonal vector of the others. Obviously, I need to make sure that they're all orthogonal to one another, which means that I can, from E, I can also recover the rotation matrix. Okay. Now, why is this called epipolar geometry? And it's called epipolar geometry because of a very interesting line, which is called the epipolar line. Let's see this. Look at this. This is a two-dimensional point on my image, right? So this is my small p equal uv, the coordinates of the image. Remember? Okay. This is my capital point, the three-dimensional point, x, y, and z. So this is 3D, this is 2D, right? We have a problem, right? When we look outside in the world with a camera like this, we have a huge problem. That p point, the image point, can correspond to an infinite number of three-dimensional points. Anyone can tell me where this infinite number of three-dimensional points are? So this small p point, right, that I see in my image, you see this point right here? Okay, maybe not. This point right here, you see that image point? They may be the image of an infinite number of three-dimensional points. Which ones? The ones on that line, right? Because if my capital P were here, it would still give me the exact same as small p. If it were here, it would still give me that p. If it were here, it would still give me that p. In fact, if I go to infinity, right, I continue this line to infinity, if I'm here, or here, or here, or here, all these points project onto the same image point. You see that? But if I have this other p prime, now this point can be the projection of also an infinite number of three-dimensional points. It could be this one, it could be this one, it could be this one, this one, this one, this one that I'm looking for, or any other point on that line, right? An infinite number of possibilities. But there's only one that's common to both. That's why I can solve the problem with two cameras. Now, let's look at this line. I still don't know what p prime is. Let's look at this line, okay? Now, imagine that I project this line. Of course, this line doesn't exist in the world, but imagine I project this line onto that second camera. That is going to look something like this. Whoops. Right? This is the image of this line of infinite possibilities for p. This line is called the epipolar line. Why is the epipolar line important? It's hugely important. Because look at this. You see this p point, this image point here? I cannot solve for capital P unless I know where p prime is. Right? You agree? I don't know where capital P is until I have p and p prime. But how do I know where p prime is in that image? It could be anywhere in that image. or could it? What epipolar geometry tells us is that it cannot be anywhere in the image. It can only be on that line that I draw. Because this P has to come from this line here, therefore the projection of P onto that image has to be on the image of that line. So only points on this line may be P prime. So once we get into the problem of finding what's called point correspondences, which means that these 2 points correspond to the same three-dimensional point, capital P, we don't have to look through matchings of that point in all this other image, but only on points that are on the line. This is a super powerful result. It's a very useful result to solve for point correspondences. So let me call this line here L prime. And now note that I can compute the other epipolar line on the other image. This would be the image of this line here, connecting P prime with P. So I would have something like this, okay? And I'm going to call this L. So I have L and L prime here. Now the question is, how do I define the epipolar line, or how do I find it? Well, let's see. How about if I tell you that you see this equation here that I have here, that this thing here is actually L. Okay? Why can I say this? Anyone sees why I can make this step? Now L, remember, in homogeneous coordinates, is the vector that defines a line. What happens if I have a linear product of a point on a line, homogeneous coordinates point P with the homogeneous coordinates of a line? This is going to be equal to 0. This is actually my equation, right? Let's see this. So remember, AU plus VV plus C equals 0, the equation of a line, right? This is the equation of a line. Now A and B in this equation are the normal vector, right? And C the offset of the line. Remember? We did that in class. So my line L is going to be given by A, B, and C, right? This is, in homogeneous coordinate, the vector that defines my line. So if I have a point P, this is U, V, 1 in homogeneous coordinates, then how do I know if P is on the line? Well, this P times L is this times this, which is equal to this equation, which is equal to 0, right? Therefore, P, this thing, has to be equal to 0, meaning that this is the epipolar line on the first image. Okay? So the essential matrix times P prime is the epipolar line on the first image. Now, what is the epipolar line L prime on the second image, this one? Anyone? It has to be this thing here, right? But I cannot write it like this. I have to transpose this. Very good. So I have E transpose P. This is my second epipolar line. So I have L equal to EP and EP prime and L prime E transpose P. These are my two epipolar lines. Okay, what else? I'm going to actually let me draw this differently. So let me redraw this so I can explain one more thing. So first image, second image. Okay. Okay, so same as before. Now the epipolar line here is drawn like this, and the epipolar line here is drawn like that. Right? This is the image of this. So if I took a picture of that line, that's what I would see. If I took a picture of that line, that's what I would see. So this is L, this is L prime. There's an additional point that's very relevant, the epipole. That's right here and right here, E and E prime. And the epipole is the point where that vector O prime crosses the image plane pi and pi prime, okay? Where this vector pinces the plane, right, crosses the plane, that we're going to call the epipole. And the epipole, along with the point P, define the epipolar line as well. Okay, so actually E is on the epipolar line, and E prime, it's on the epipolar line prime. So if I use now this equation that I have here, say E transpose this part here, E transpose P, right? But for P, I'm going to take a point on that line, let's say E, my epipole, okay? If I take my epipole, then this is equal to, remember, this would be the rotation transpose Tx times E, and I know that this has to be equal to 0, right? Now, this is not 0, this is not 0, right? So this has to be the null space of this thing here, right? And that means that if I compute the eigenvectors, meaning that if I compute the eigenvectors of E transpose, in that case, then the epipole is given by the eigenvector that has eigenvalue equal to 0. Very good. Okay, so the epipole is equal to the 0 eigenvalue, or the eigenvector associated to 0 eigenvalue of E transpose. And obviously, similarly, E prime, it's the eigenvector associated to the 0 eigenvalue of E. Okay? Okay, so far so good. Now, this, remember, is assuming that the cameras are calibrated. Now, more often than not, as you found out in your first project, cameras are not calibrated. When we don't have the cameras calibrated, we can still use this, but we have to redefine the essential matrix to also include the calibration of the camera, the parameters of the calibration of the camera, the intrinsic parameters, okay? K, remember, matrix K. So that matrix is going to include both the intrinsic parameters and the essential matrix. What's more essential than the essential matrix? I know what's more essential than essential. Let's call it the fundamental matrix, okay? So the fundamental matrix, capital F, includes the essential matrix and the intrinsic parameters. So let's see that. So the fundamental matrix, same equation as before, but now instead of E, I have F, still equal to 0, where now F, it's equal to my essential matrix times the matrix of intrinsic parameters, right? And then, of course, to multiply matrices, as you know, you need to multiply on both sides. So I'm going to multiply. This is the intrinsic parameters of the second camera and the intrinsic parameters of the first camera, right? So that defines my plane pi. This defines pi prime. And I need to compute the inverse, obviously, of both. And this one, I need to transpose it in order to make this equation work. So this is the same thing, the fundamental matrix, as the essential matrix. Everything that we have said for the essential matrix also applies for the fundamental matrix. Everything, the epipolar lines, the epipoles, right? The epipoles in that case would be Fp prime is the epipolar line. On pi. And F transpose P, the epipolar line on pi prime, and the epipoles are F transpose, which is the eigenvector associated to the 0 eigenvalue of F transpose, and the eigenvector associated to the 0 eigenvalue of F, right? These are my epipoles.
To P transpose F, that's P prime of P.
Oh, P prime, yes. Thank you.
And what does K minus T?
This is the matrix of intrinsic parameters. This is the matrix you've been working on your project, right? That has these, depending on the parameterization that you do, but with this specific parameterization here in class, gives you that matrix of the intrinsic parameters. This is for the first camera, or the matrix that defines the plane pi, and this is the one that defines the plane pi prime, or the second camera. Okay?
What does the superscript minus T?
This is, you have to compute the inverse of this, and this is transpose. Right? You have to transpose that inverse. All right, so going back to the paper I'm going to post in Carmen, Longet-Higgins paper has the first algorithm. He defined the very first algorithm, Longet-Higgins, to solve this problem. And that's called the 8-point algorithm. So let's see why this is called the 8-point algorithm. Okay. Now F is a 3x3 matrix, right? Right? Okay, so how many unknowns do I have? So remember, I need point correspondences P and P prime to solve for F. So how many unknowns do I have? 3x3. It's not a tricky question. 9. Thank you. Right. Okay. But F, it's defined up to scale. So I can fix one of these 9 unknowns to whatever number 1 I want, right? And therefore, I have 8 variables that I need to estimate. How many equations do I need to solve for 8 unknowns? 8 equations. If I need 8 equations, how many point correspondences do I need? 8. That's why it's called the 8-point algorithm. Okay. So given my points, let's call them PIs, right? Given by UI, VI, and 1, I can build this multiplication of my 8 points. So I have U1, V1, 1. That would be my first point. U2, V2, 1, and so on up to 8. Now here I have F. F, remember, is 3x3. So I'm going to have F11, F12, F13, F21, F22, F23, whoops, what am I doing? I'm in the mood of writing this. Okay, F31, F32, F33. And now this multiply by my P primes. So same as this, but with primes. So I'm going to have U1 prime is transpose. This one is transpose. This one is not. So U1 prime, V1 prime, 1. U21, 2 prime, V2 prime, 1, and so on. U8 prime, V8 prime, 1. Okay, there we go. And this is equal to zeros, right? Just going to write 0 as a vector of zeros. Okay. Now remember that this is too many unknowns. This is 9 unknowns, but we know that this is defined up to scale. So I'm going to eliminate one of them. Generally, people eliminate the last one and just write a 1, right? So this is 1. Just going to fix this number since it's defined up to scale. And now, if you do this multiplication and you solve the system of equations, then you end up with the solutions for F11 through F32, right? You end up with enough equations. If you prefer, you can also write this in our most common way of writing this equation as from 1 to 8 pi transpose f pi prime square, right? We can also write it like this and solve it as we have done before. Simple system of 8 equations, 8 unknowns. Now, you have a problem with this system. You need to guarantee that all equations are linearly independent, right? So Langett-Higgins, in his Nature paper, he goes into details about how to iterate the system so you guarantee that you get point correspondences that give you independent equations. Okay? All right. The problem is that cameras are not pinhole cameras. At least last time I checked, my cameras are not really pinhole cameras. They have lenses. And the modeling that we have done makes a number of assumptions that are not generally true. So depending on which 8 points I use, I'm going to get one solution or another. Right? I'm going to get different solutions depending on the points that I use. Do we know of a way to solve this problem of using more points and getting the best possible solution out of many points? So instead of 8, what happens if I have more points? N. And I define this as an error. Do I have now a way to minimize that error function? Thank you. We can use linear least squares, right? So what you implemented in your project, right, or your homework, you can use the same algorithm that you have on that equation to find the eigenvector associated to the smallest eigenvalue, which is the error, right? And that eigenvector defines the entries of F. That's it. Okay, there are many variants to that. Obviously, as you can imagine, this is the fundamental algorithm or the main algorithm. But there are ways to improve over that. So for example, I can parameterize F. This is one possible parameterization. It's not the only one, but this is one. Okay, so I have BA, negative AB minus B alpha, negative D, negative C. Oh boy. All right, my notes, I'm missing something here. You can check in the slides, they're online. D beta prime, B alpha, C beta prime, A alpha, and the last one is negative C B prime minus D B prime alpha plus alpha beta alpha prime plus B alpha alpha prime. Okay, good. Where the epipoles E and E prime are given by alpha and beta, and alpha prime, beta prime. Okay. And the other entries are just constants, A, B, C, and D. Okay. So one extension of the least squares solution and the 8-point algorithm here takes advantage of this parameterization as follows. It first uses the 8-point algorithm to compute F. Okay? Then from this, once you have F, you use that parameterization that I've given you there to define or compute E and E prime. Again, to do that, what you're going to do, you're going to compute the eigenvalue decomposition of F and take the eigenvector associated to the smallest eigenvalue, right? That gives you E and E prime of F and F transpose, right? Now, once you have this, you substitute alpha and beta and alpha prime and beta prime in that F equation, right? And that gives you, I don't know, let's call it F prime, okay? Is the new fundamental matrix the new F with these epipoles. And then, once you have this, you minimize the error function of least squares. Okay. Simple extension that takes advantage of everything that we have introduced today. Okay? Let's see what else we can do. Now remember, in our first image, defined by the plane pi, we had our pi, right? A pi, and obviously corresponding pi prime in the second image that allowed us to compute our solution for f, right? So with that, we've solved for f with one of these algorithms here, the 8-point algorithm, the linear least squares algorithm, or this latest algorithm that I've defined here. Okay? You compute f. Now, given f, we can compute the epipolar line, right? Remember how to do that? F times this pi prime, right? So I compute the epipolar line. And whoa, what just happened? Oh, that's bizarre. Pi is supposed to be on the epipolar line, but it's not. Why? Because our computations are not perfect, right? First off, they're based on data points. These data points may have errors, and the model of the camera is not really the camera. So there's going to be a distance between the epipolar line and that point P. Let's define that distance d as the distance from pi to f pi prime, right? Okay, this is the same as saying the epipolar line, L, right? Now, in reality, what I want to minimize the following error function. If I consider the square of that distance, pi f pi prime, right? And I sum over from 1 through n, right? I want to minimize this new error function. I can even do better than this. I can also add the distance from pi prime to the epipolar line L prime, which is defined as F transpose pi, right? So I have this equation, and now I want to minimize E. Unfortunately, there's a problem here. This is no longer a linear equation. That's now a nonlinear equation. How am I going to do that? I'm going to do that with a method that very smartly it's called nonlinear least squares. Okay? All right. So let's see. Oh, yeah. Good. So let's see if I can cheer you up a little. Okay, so you look very confused or overwhelmed by all the amount of information that I've been giving you here about the essential matrix, the fundamental matrix, and everything else. Don't feel bad about this. Everyone does, right? Because so much information. So a group of graduate students in Australia decided to have a song.
Fundamental matrix is displayed geometry. A matrix with 9 entries. It's square with size 3 by 3 has 7 degrees of freedom. It has a rank deficiency. It's only on rank 2. Roll a matrix F and you'll see 2 points that correspond to column vectors called x and x prime. X prime transpose times f times x equals 0 every time. And constraint equals epipolar lines. Rules multiplying f by x results in vector L prime. It's the epipolar line. The other 2 passing through x prime. The 3 component vector. Homogeneous design. The left and right null spaces of them are the epipoles E prime and E. All of the epipolar lines should pass through these. Here's a linear special example. Take 7.8 samples, construct the matrix, take the SPD and the elements again for the last copy.
All right, go to YouTube and just write the fundamental matrix song. You'll find you can play it as many times as you want until you remember all the details. As you can see, you're not alone. All right, so now that you know how to remember all these details, let's see how we can solve the nonlinear least squares problem. So to see that, let's consider a set of functions, f1 of some q variables, x1, x2 through xq. And as before, we're going to have p equations, but now these equations are nonlinear functions of x1, x2 through xq, and all of them equal 0, obviously, as before. Okay? So that's my new system now of nonlinear equations, each equation defined by a function f, nonlinear function f, and each fi, it's a mapping from q dimensions to, or p, no, q dimensions, right, to r. Now, you can also define f as the vector of all functions, so f1 through fp. And x, it's our vector, as always, x1 through xq. And of course, we want f of x equals 0, right? F, now this vector. Okay? All right. Now, as before, as we had in linear least squares, when p is larger than q, right, meaning the number of equations is larger than the number of unknowns, there is no solution, right? So in that case, we can define our error function that we have been using, the least squares function, which remind me, I think it's f of x squared, right? Which is the same as saying that fi square of x from 1 through p, right? Now, since I cannot use the linear solution, I need to find a mechanism to determine what the minimum of that function is. And remember, how have we done this before? We equal the derivative of this function to 0, because the derivative of the function at 0 means that I'm at a minimum or maximum, or a saddle point, right? So here's what we're going to do. All right, is anything working here? All right. X or f of x, right? Here, and here's my error. Come. And now this function is going to look something like this, right? And all I can expect to get or to arrive to is at some minimum, okay? So for all the minima I have, I'm going to find a minimum. This is what I'm looking for. This minimum here. And this, I know that the derivative of this at that point is actually 0. So let's see how we can do that. I'm going to start with the classical approach to solving a nonlinear problem by linearizing the problem with a Taylor expansion. Okay? So the Taylor expansion of f(i)x plus some differential of x, and I'll explain why this in a second, it's equal to f of x plus differential of x, partial derivative of fi with respect to x1 of x, and so on up to delta x. This would be x1, xq, the partial derivative with respect to xq of x. OK, excellent. Plus all the orders larger than 1 of d of x, delta x. And why do I want to do this? Here's the trick. The reason I want to do this is because I want to look for this minimum here, right? This value here for x. Or let's call it x star if you prefer. But I don't know what it is. So I can start at some point x and then add some dx, which will move me in either this direction or that direction. And that is what this represents, right? So this represents how I'm moving in one of these two possible directions. I add or subtract a small number to x. And what's this equal to when I do this with that Taylor expansion? This is approximately fi of x plus the gradient of fi of x dx, right? Because this f1 x1, the partial derivative of fi with respect to x1 with respect to xq, it's nothing else than the gradient. That's what this is called, right? So again, here, the gradient of fi of x, it's equal to a vector of partial derivatives, right? Okay. Transpose. Okay. So to compute this in practice, we're going to use the Jacobian matrix. The Jacobian matrix, remember, is nothing else than the matrix of partial derivatives, right? So the Jacobian matrix, let's call it J. It's equal to, it's a matrix that has all the partial derivatives. So this is f1. So now I'm going to use this gradient here, but I'm going to substitute sub I for 1. So I have partial derivatives with respect to of f1 with respect to x1 and all the way to xq. And now I'm going to repeat these rows for every possible f, and I have p. So fp with respect to x1 and fp with xq, and that's my Jacobian matrix, right? Of all the partial derivatives for my function f, right? Where my function f, it's a vector of functions f1 through fp. Now, what does this mean in practice? In practice, look at this. In practice, this equation here means nothing else than fi of x plus the gradient, right? What is the gradient of this function? This is the gradient of the function, right? Correct? And where is the gradient pointing me to? It points me toward the minimum, where the derivative is 0, right? So what I'm actually doing here is I'm adding the gradient times a scalar, right, the amount that I want to move from the current point that I have to move me closer to a local minimum. Okay? All right. So with that, I can write that fx plus delta x is approximately f of x plus the Jacobian that I have computed here of my function f of x times that small number delta x. Okay? That's what I'm doing. Now with that, we can derive an algorithm that's called Newton's algorithm or Newton's method. So let's write this down. So remember that we are using this because we know the partial derivative or the derivative of the function is going to be 0 at the minimum. And we're going to define an algorithm that iteratively gets us closer and closer to that minimum. Okay? So the way we're going to do that, we're going to use the Jacobian that we just defined. So I'm going to use the Jacobian defined here of x times f of x. That has to be equal to 1/2 the gradient of the function, which has to be equal at our minimum. What is this equal to? 0, right? For this to be a minimum. So if I define, say, f of x, it's equal to the Jacobian transpose times my function, and I differentiate this expression, I get j of capital F of x, it's equal to jf transpose of x times jf transpose. So all I'm doing here is differentiating, plus the sum of my fi's times h of fi of x, where h is, anyone? The Hessian or the matrix of the second derivatives. Very good. So let's write this down. The Hessian the Hessian matrix Fi of x is given by the second partial derivative of our function Fi. So this would be first with respect to x1 squared. So differentiate twice with respect to x1. Then x1, x2, x1, x3, all the way to x1, xq, right? And then I do this for all the possible q's. So here I have fi xq, x1. And here I'm going to have xq squared, right? Right? Okay? Now what does this do? The Hessian, which is the second derivative, actually tells me how steep this function is, right? So it's not the same if I have a function that looks like this, that if I have a function that looks like this, right? Second derivative tells me the acceleration, right? So it depends on how fast this is dropping, or depending on how fast this is dropping, I want to move faster or slower, right? I want to be careful, because if this is dropping really fast and I move in this direction really quickly, this is what could happen. I move really quickly from here to here, or even worse, from here to here, right? And I have actually missed my point that I'm looking for, right? So that is what the second derivative accounts for. It accounts for the acceleration of the function, okay? All right, so putting all this together, let's write down the final algorithm, Newton's algorithm. So remember we have, okay, this is not going to work. Remember we have x plus delta x. It's equal, or approximately, I guess I should say, right? It's approximately fx plus the Jacobian of f of x dx, and that basically, if we move things around, that gives us the Jacobian of x, f of x times dx. This is equal to negative the function of x at my minimum, right? Because I want this to be equal to 0. And that means that the Jacobian, so remember this is f, but now I want to compute that capital F that is defined there on the other side. This has to be equal to capital F. And that means that the Jacobian of capital F is defined by the Jacobian of F transpose the Jacobian of f plus my sum of the functions times the Hessian. Okay. So this is my equation that I want to solve for. Substituting this here, right, gives me the equation, the system of equations to solve as before. This leads into an iterative algorithm. As I said, you start with some original estimate, and Newton's method will tell you how much to increase or decrease your value to get closer and closer to a minimum. There are a variety of algorithms in optimization that have been proposed to solve this problem, right? I'm not going to cover this in detail. Obviously, this is covered in optimization classes. But in MATLAB, if or when you need to use this in your homework and projects, in MATLAB there are several functions that allow you to do this. F mean bounded. This is bounded least squares, and it has 3 entries. So you can make f mean b and d of your function, rather, not vector, your function now f x1, x2, where x1 and x2 define the bounds in which you want to find the solution, so that your solution has to be larger or equal than x1 and smaller or equal than x2. Okay. So this is one function that you can use in MATLAB. There's another function, f min con. This is a constraint least squares, and that has 4 inputs. So x equals f min constraint of f x0, a, and b, where here x0 is the initial point at which you want to start. And a and b define the constraint, right? And your constraint is that a times x has to be smaller or equal than b. Okay? And again, x0 is your initial point. One more. F mean unconstrained. So this is unconstrained least squares. And in that case, I have only 2 inputs. And this is the same as the constrained one, but without these 2 inputs because I don't have a constraint. Okay? All right? Any questions? Nope. Yeah, question over there?
Using that, when we got that error function, like using the gradient descent, we'll only be able to go to the local minimum.
Say that again?
Using the gradient descent approach, we'll only be able to go to the local minimum.
Yes.
But don't we need the global minimum?
Okay, very good question. So here's the question. Very good question. The question is, what happens with that method if I have a function like this? Actually, let me do it like this. Okay, this is my function, and my starting point is right here. Okay, so that's my initial estimate x0, and then I compute the gradient. The gradient is going to be like this of my function, right? And that's going to allow me to find this minima here. Right? I find this minimum right here. But there are other minima in my function, right? And for one, this one right here is a minimum that is lower or has a smaller number than this one. And this method does not guarantee me that I find the global minimum. It only guarantees me that I find a what's called local minimum. Okay? So locally, in that region of my space, that is the minimum there is. But globally, throughout the whole space, there could be other minima that are even of lower value than the minimum, the local minimum I'm at. Right? That method will never get you out of that local minimum, because once you are here, the gradient doesn't allow you to go in either direction, because this gradient points in this direction and this gradient points in this direction, right? So you're stuck. So that's one problem, and we just have to deal with it. Okay? The other problem is that you might have a saddle point like this. And then maybe there's a really good minimum here, right? So this is the minimum I want to attain. But once I'm in the saddle point, the gradient just becomes 0, too, right? So at that point, I'm also stuck at whatever I get. So these are problems that these methods, these nonlinear least squares methods have. And there's no solution to that, or no easy solution. Any other questions? All right. I'll see you next time.